Assalamu alaikum students. Today we are going to start the third lecture on the course called Statistical Physics 1. In previous lecture we discussed the macroscopic version of the second law of thermodynamics, where we discussed two definitions of second law given by Kelvin and Clausius. And we saw that the second law is based on the general assumptions that the heat always flows from a body at high temperatures to the body at low temperatures. And we saw that there is some particular direction in which our system wants to go, and we found that that particular direction is the direction of increasing entropy, that the entropy of the universe always increases. We discussed that for a reversible process, the entropy of the system, uh, the change in entropy of the system is zero. That is, there is no change in entropy. Whereas for an irreversible process, the entropy of the universe always increases. So, but that macroscopic version only tells us that the system wants to go towards the direction of increasing entropy, but it does not give any physical insight that why a system wants to go um, from a body at higher temperature to the one at lower temperature. So that explanation is given by the second law, or the microscopic version of the second law of thermodynamics, that was given by Boltzmann, and it is based um, uh, um, uh, on on his mathematical expression that S is equals to the KB log of W. So we are going to discuss that. So let's discuss the second law of thermodynamics, and the good thing is that you don't need any uh, physics to understand the microscopic version of second law. So you can have the understanding of second law just by your uh, general understanding. So let's consider a dice. Let's consider a pair of dice, and for example you are interested in the sum on both these dices. So let's suppose you roll a pair of dice and you get 5, and we know that there are different possible ways to get 5 on this pair of dice. That is, you can get 5 on this pair of dice, that is, you can have 1 on the first die and 4 on the second die, or you can have 2 on the first die and 3 on the second die. And there are two other ways as well, that 3 on this die and 2 on this die, 4 on this die first one, and 1 on the second die. So there are 4 different possible ways to get a total number 5. But what you will see here is that each time you throw this pair of die, you cannot predict the outcome. The outcome is always a random number. But you will see that when you throw this die 1,000 times, you will see that you will get a very beautiful predictable pattern, that you can predict about the number which is going to come. But in very few throws you will not be able to predict that which number you are going to get. So let's suppose that we throw this pair of die the 1,000 times or 10,000 times, and then we enumerate all the information, that how many times we get a sum of 2 and how many times we get a sum of 6 or 12. And then we plot a graph between the number of times for each sum against versus each sum, and you will see that you will get a very symmetric, beautiful pattern. We know that since we are using a pair of dice, so we can have an outcome of 2, 3 up to 12. The maximum, this is the maximum possible outcome that we can get with a pair of dice. And the most probable number that you will get with this pair of dice, when you will throw it 1,000 times, you will see that this is the number which is 7, which you are going to get most of the times. And the number that you get will get at the least of the least times is the number 2, or the number 12. So what's the reason behind that? So you can easily understand it. What we saw here is that the outcome of a single row throw um, is random, but the outcome of a collection of large number of throws is a beautiful predictable pattern. And this pattern can be understood on the basis of this observation. We know that the total outcome of 2 on these two dice is there is only one way to get a sum of 2. Whereas also in order to get 12, there is only one possibility in by which you can get a sum of 12 on both these dice. Whereas the maximum possibility exists for the case of 7, that there are 6 different possible ways in which you get a total sum of 7. So when you are throwing the dice um, for many times, so this is the most probable outcome that is going to come, that is you will get 7 most of the time. So this is the most probable outcome, and whereas 2 and 12 are the least possible outcomes. So what you understand from this example is that what nature wants to do is that the nature always tries to move towards the most probable state, which is 7 in this case. And the second thing that you that I want to discuss here is that you will see that all these outcomes are possible, that you can even get 2, you can even get 7, or you can even get 10. So it means that all the outcomes are possible. So you can say that the second law of thermodynamics is is not an absolute law, since all the possible it can since all the outcomes are possible. So it is not an absolute law, but it is a statistical law. Okay, so that's a very important point to note here, as that the first law is always right. So it is an absolute law, whereas the second law is a statistical law. So now let's discuss about the mathematical expression that was given by the Boltzmann. And the Boltzmann defined entropy S is equal to Kb log of W, where Kb is known as the Boltzmann constant, and W is the number of ways in which you get a certain outcome. So that is, the W is the number of possible arrangements in which you get a certain possible outcome. For example, here in this case, the outcome is 7, and so there are 6 different possible ways in which you can get this number. So that means that, so higher this number W, higher will be the entropy of the case. So what nature wants, that when what is happening when the entropy of when we say that we say that a body at higher temperature always loses heat to the cold body, and we observe from the macroscopic version, we say that this is the case that entropy of the system is increasing when system is when heat is going from a body at high temperature to the one and at lower temperature. But what microscopically we can understand here is that the nature moves towards the most probable state when we say that the entropy of the system is increasing. So that's it about the second law of thermodynamics. We will also uh, discuss a bit more later in this lecture. So let's now come towards the concept of a microstate and a macrostate. A microstate is defined as a system, as a state of a system, which is defined as a state of system in terms of the states of individual particles, whereas a macrostate defines a state in terms of the macroscopic variable, for example, the number of particles, pressure, volume, temperature, internal energy, etc. So in order to get more insight about the microstates and macrostates, let's consider this example. Let's consider that you have a two-state system, that is state 1 and state 2. You have 2 particles in state 1 and 2 particles in state 2. All these 4 particles are distinguishable. So this is one possible arrangement of the system. That is, you can have first or second particles in state 1 and third and fourth particle in state 2. So this is one possible microstates, that is which defines the states of the individual particle, that is particle 1 and 2 exist in state 1, whereas the particle 3 and 4 they exist in state 2. But we can see that there are six different possible arrangements that we can make to distribute these two particles in these two boxes. That you can have 1 and 2 in the first box, 3 and 4 in the second box, and similarly you can have 1 and 3 in the first box and 2 and 4 in the second box, and similarly 2 and 3 in the first box and 1 and 4 in the second box. So there are six possible six different arrangements that you can get with two different particles in these two boxes. And the point to note here is that all these particles are distinguishable, so that's why we can distinguish that 1 and 2 are present in this state 1 and 3 and 4 are present in this state 2. So we can see that what we will say here that 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 these individual particles have different states in all these cases. So it means that you will say that there are six different possible microstates for this system, whereas there is only one macrostate. In macrostate, you are interested only about the macroscopic variable, which is the number of particles in this case. So there are four particles in total and two particles in each state, that is state 1 and state 2. So there is only one macrostate, and for this macrostate contains a total of six microstates, that is six different arrangements for individual particles. So that's the concept of the microstates and a macrostate. It will also help you out to develop further understanding about the second law of thermodynamics. So let's discuss more about the concept of microstate and macrostates, and let's consider a question that what happens when a system goes from a non-equilibrium state to an equilibrium state. We know that whenever a system goes from a non-equilibrium state to an equilibrium state, it always tries to increase the entropy of the system. That is what it is trying to do is that it will try to distribute the particles equally in the whole space, in the whole available space. So let's discuss this problem step by step. And let's imagine a gas in a container with a left hand side and a right hand side, and we are going to find this particle. And let's suppose that we take a snapshot of the particle, and we will see that since there are two compartments, the 1 and 2, so at one time the particle can be found in this left side, whereas if you take the snapshot after a certain time t, you will find this particle on the right hand side on the right side of the box, on the right box. So it means that there are two possibilities for this one particle, that either this particle can present on in the left box or in the right box, and these two possibilities are equally likely. Now let's consider that you have two particles. So this was the case of the one particle, and now let's suppose that you increase the number of particles, and the number of boxes are the same. So let's enumerate the cases that you can get for these two particles in two boxes. So the first case possibility that you can have is that you can have both particles A and B on this left box. That is both A and B particles are present in this left box, as these are also this information is also summarized in this table on the right. And whereas the second situation is that the particle A is on the left box, the particle B is on the right box, and similarly you can get the other way around, that the particle B is on the left box and particle A is on the right box, or finally you can have both particles A and B on the right side of the box. So it means that there are total of four microstates. The first macrostate is one that in which both particles are present on the left side of the box. The second macrostate is the one in which both particles are present in the right side of the box, whereas the third macrostate is one in which both the particles are present in both boxes. So this second macrostate contains two different microstates, and since the probability of each microstate Same. So for the first microstate, that is the two particles on the left hand side, you will have a possibility of this microstate will be equal to 1 by 4. For this macrostate, the total probability is 1 by 4, and there is only one macrostate for the system. Whereas for the second and third case, this is a common. This combination will represent the second macrostate, which contains two microstate, and each have a probability of 2. So if I talk about the total probability of this macrostate, so the total probability of this macrostate will be equal to 1 by 2, since 1 by 4 is the probability for the upper microstate, and 1 by 4 for this third macrostate, and the sum will give you 1 by 2. And similarly, the third macrostate will also give the probability of 1 by 4, since there are total 4 different arrangements that you can make with the two particles in two boxes. So now let's increase the number of particles from 2 to 4, and you will see that the first possibilities that you can have is that all four possible particles are present in this left side of the box, and other possibility is that you can have all of these four particles on the right hand of the side, and there is only one possible micro. W represents the number of microstates of the system, a number of microstates for this macrostate. So there is only one microstate for the for this first macrostate. Whereas if we consider the second case, that is the three particles on the left box and the one particles on the right side, you will see that you can make four different arrangements with these particles. Since these particles are distinguishable, you can distinguish between these particles. So you can either have the particle A on the right box, the particle B on the right box, you can have C on the right box and remaining three on the left side, or you can have D on the right side and remaining three on the left side. So there are four different possibilities in which you have three particles on the left side and one particle on the right side. And similarly, there are four possibilities for the case that you have one particle on the left side and three particles on the right side. Whereas for the 2 case, that is the two particles on the left side and two particles on the right side, there are six different possible arrangements in which you get this 2 configuration. So you will say that this macrostate, which contains six microstates, is the most probable macrostate of the system. That is, half on each side is most likely macrostate which can exist. Whereas the first and last macrostates are least probable, since there is only one arrangement in these four particles can be arranged on the right hand side of the box or left hand side of the box. So now let's increase the particle from a total of 4 particles to 10 particles, and you will see that the first possible macro state is that you have 10 particles on the left side and 0 particles on the right side. The first and there is only one arrangement in which you can do that, and that arrangement is that all those particles are on the left hand side of the box. Whereas the second macro state which can exist is that either 9 particles on the left hand side and one particle on the right hand side of the box. You will see that there can be 10 different possible ways in which you can get a total of this number, that is the 9 on the left hand side of the box and one particle on the right side of the box. So these total arrangements will be 10. So there are 10 microstates for this one macrostate. And similarly, if you have 8 particles on this left box and 2 particles on this right box, you will see that you can arrange these 10 particles with this configuration in 45 ways. So it is not easy to understand that how you can make these 45 arrangements, but this 45 number can be calculated very easily by using the concept of commutations and permutations, which we are going to discuss in our next few lectures. We know that for commutations, if write it as 10c8, which is equal to 10 factorial over 10 minus 8 factorial into 8 factorial, that will give you a number of 45. Or if you can write it as 10c2, it will also give you a total of 45. So it means that there are 45 total possible microstates for this macrostate. And whereas for this macrostate, that is the 5 particles on left side and 5 particles on right side, you can have 252 different arrangements in which you can arrange 5 particles on left side and 5 particles on right side. And again, you can uh, get this number of 252 by simply using the concept of commutation. And so since there are a total of 10 particles, so you will write that 10c5, which is equal to 10 factorial divided by 10 minus 5 factorial 5 factorial. And if you will solve this number, you will get a total of 252. So there are 252 different microstates for this macrostate, and you will see that this is the most probable macrostate in which the system will exist. So this is the most possible macrostate, since there are maximum number of microstates which exist for this system. And whereas the case for the first and the last one, that is the 10 particles on left or right side, these two cases, these two macrostates are least probable, since there is only one way of having 10 particles on left side or right side of the system. Now let's think that what we are doing is here is that we keep the number of boxes same, and we are increasing the number of particles from 1 to 10. And now we know that in case of in real systems, for example, in case of solids, you have a large collection of atoms, that is Avogadro's number of atoms. So what is going to happen when you have such a large number of atoms in a system? So where uh, how the particles can distribute some space in that case. So if you have Avogadro's number of particles, it is highly unlikely that we will get all particles on left side or all particles on right side. What will be the most probable is that the half on each side is most likely, as we discussed in this previous case, that five particles on this space on this in this case is the most probable outcome. So it means that when a system goes from a non-equilibrium state to the equilibrium state, what it always tries to distribute the particles equally in the whole available region. So now let's come towards the mathematical definition of the second law of thermodynamics given by Boltzmann, which is equal to Kb log of W. So it means that higher this number W, the maximum, the higher will be the entropy of the system. And you can have more and more entropy, or you can have higher entropy by varying different parameters. For example, if you increase the volume of the system, it means that there will be more microstates available for these particles. So definitely W will be more, and you will have more entropy. And similarly, if you increase the temperature of the system, so when you increase the temperature of the system, it means that you will have more available energy states. So more energy states, it means that more microstates and more entropy. सॉरी, हाँ आएंगे, वो लैपटॉप अभी यहाँ पे पड़ा हुआ है उनका. So similarly, the next case is that if you have more number of particles, in this case, if you have more number of particles, as we discussed this example, you will have more microstates available, and hence more entropy. So the entropy of the system can be increased by different possible ways: by increasing the volume of the system, by increasing the temperature of the system, or by increasing the number of particles in the system. So from here we are now clearly say that when a system goes from a non-equilibrium state to an equilibrium state, what a system tries to do is that it always tries to increase the entropy of the system by increasing the number of possible microstates of the system. So, and that can be achieved only that when when all the particles are distributed equally in the available state. So in previous example, we considered that all those particles are distinguishable from each other. That is, we can distinguish between the particle one or the particle two. But we did not discuss about the indistinguishability of the particles, because in reality we don't know, we cannot distinguish one particle or one atom from the other atom. So in that case, so let's find that what is the difference this um, is going to make here. So for the distinguishable case, that is for the case of two particles in two boxes, there are four different microstates that you can have these two particles on the left or on the right side, or one particles in each side. But what difference it's gonna make when you say that both these particles are indistinguishable? So when these particles are indistinguishable, you cannot distinguish which one is this first particle or which one is this right particle. So what you can only say that there are two particles on this left side and zero particle on this right side. The second possibility that you can get is that there is one particle on the left side and one particle on the right side. So in this state, there is only one possible microstate. You cannot have right or green here or green or red here in this case. So what you only know is that you can have one particle in each box, since you cannot distinguish between these particles. And the third possibility is that you have zero particles in this left box and two particles in this right box. So it means that when as you have indistinguishable particles, the total number of microstates of the system, they will always decrease. So we can also predict, or we can also find out the total number of arrangements in both cases. For example, for the case of distinguishable particles, you can have total number of four arrangements, and this can be figured out by making this formula that 2 power 2 will give you 4. And if you have three particles in these two boxes, it means that you should have a total of eight possible microstates for this system, since in that case you will have a 2 power 3, which will give you 8. And similarly, in this case, you can also make a formula for the total number of arrangements. That is, for these two particles in two boxes, you have total arrangements of 3, which is equal to the sum of 2 plus 1. Similarly, if I say that you have three indistinguishable particles, and these three indistinguishable particles are to be distributed in these two boxes, it means that there will be only four possible arrangements. That is, this four sorry so in this case, man, the total arrangements is 3, which is equals to 2 plus 1, and in that case the total arrangement should be 4, which is equals to 3 plus 1. So this number 2 or 3 will represents the number of particles, plus 1 will give you the total number of microstates in the case of an indistinguishable particles. So now let's discuss another example to further develop this concept of microstate and macrostate towards the physical systems. And let's consider a molecular system, and suppose that we have three non-interacting identical molecules distributed over different energy levels. And it is given that the particles are distributed in such a way that the total energy of the system is 3. So we are going to discuss that how many different ways can uh, we get this total of total energy equal to 3 electron volt. So the first possible arrangement in which we get a total of 3 electron volt for these three particles. Is this arrangement that this represents these numbers 0, 1, 2, 3 represents the energy of energy associated with each level. So it means that you can have 3 electron volt for three particles for an arrangement that all these three particles are present in the second level where the energy is equal to 1 electron volt. So 1 electron volt for each particle will give you a sum of 3 electron volt for three particles. So this is the first possible macro state, and there is only one micro state for this system because there is only one arrangement in which you can arrange these three particles to get a total of 3 electron volt. And similarly, the next possibility in which you can get a total energy of 3 electron volt is that you can have and the first particle in first level where the energy is 0, the second particle is in the second level where the energy is 1 electron volt, and the third particle is in second level where the energy which has an energy of 2 electron volt. So the sum of the energy will be equal to 3 in this case again. So this is the second macro state, and this macro state can be achieved in um, six different possibility, six different arrangements that you can have this particle here or C particle here, or you can in this way you can have one particle in these three levels in six ways. So it means you will say that you will have a total of six microstates for this second macrostate. And similarly, the third option in which you can get a total of 3 electron volt is that you can have two particles in energy level 0 and one particle in energy level which has a 3 electron volt energy. So the total energy for this system is 3 electron volt. So this is the macro state 3, and there are three different possibilities for this macro state. That is, you can have either the particle A here, or you can either have a particle B in this third level, or a particle C in this third level. And this third level means the level which has an energy of 3 electron volt. So it means that you have if you want to distribute three different non-interacting particles um, in a system which has a total energy of 3 electron volts, so you can have three macro states, so you can make three macro states for that systems and for that system, and three macro states contains a total of 10 microstates. That is, for the first macrostate you have only one microstate, for the second macrostate you have a total of 6 microstate, and for the third macrostate you have a total of 3 microstates. So it means that you total have a 10 microstates. So if I ask you to find out the probability of the first macrostate, so the probability of the first macrostate will be equal to 1 by 10, since there is only one microstate for this system, and whereas the probability for the second macrostate is equal to 6 by 10, since there are six different possible outcomes for this second macrostate. And similarly, the third macrostate will have a probability of 3 by 10. So now we are in position, we have discussed uh, uh, we have now developed our understanding about the macro state and micro states of a system. So now you are in position to understand that to answer this question, that why a body always releases heat from hot object to the cold object. So for that, let's consider two particles. Let's suppose that the one particle has an energy of 3 electron volt, and the second particle has an energy of 1 electron volt. These bars on these particles represents the energy of the particle. And since we know that energy of a system is always quantized, just like the charge of a particle is quantized, we will see in case of black body radiation spectrum that the energy of the system is always quantized. And that is, the Planck's explained the black body radiation curve by assuming that by considering that the energy of the system is always quantized and given in terms of quanta of the particles. So let's suppose that now consider that in how many ways we can distribute this total energy in these two particles. Um, so the first possibility, which is the first possibility that we can have, is that that this uh, that is for particle 2, one quanta of this particle 2 is shifted towards the particle 1, which always has which always have three quantas available with it. So this is the one possibility. But what our most probable situation is that the second particle has the first quantum stick with it, but you can have this red quanta which is associated with particle 1, and it can move towards the particle 2. Or there is a possibility that this black quanta associated with particle 1 can move towards the second particle, or this green quanta can move towards the particle 2. So it means that there are more possibilities available for this particle 1, which has higher quantas available with, I mean, which has higher energy. So it can, so there are more possibilities available with this particle, that it will shift its energy from to the other particle. So it means that we can see here is that there are different possible arrangements that we can get, and the most possible and the maximum number of arrangements that we can have for these two particles is that we can have two particles on particle 1 and two particles on particle 2, and we can have different arrangements for these quantas. So it means that um, uh, this is the most possible situation and the most probable situation, whereas this situation is least probable, where the particle 2 don't have any quanta and the particle 1 has all this energy associated with it. So it means that when what will happen is that the system always wants that when a system uh, um, uh, exchanges heat from a hot object to the cold object, it tries to reach in equilibrium to equilibrium. And in going towards equilibrium, what it tries to do is it tries to distribute the energy equally, which maximizes the entropy of the system, since there are maximum possible arrangements which are available for this case. That is, if we apply the microscopic version of Boltzmann, S is equal to kb log of W, so we'll have maximum entropy for this case. So now we can, so this is the reason that why the entropy of the system increases. It increases because the system always wants to go or wants to move towards the most probable state. So now let's consider another problem, uh, and let's this is a problem uh, in which we will explain that the entropy of the system always increases. We did that in previous lecture using the macroscopic version. Now we will do this with the help of the microscopic version, where we will see that the entropy of the system always increases. So for that, let's consider that you have two blocks, that is the block 1 and block 2. Each block contains four particles, and let's suppose that this first block has a 3 electron volt energy, whereas the second block has 1 electron volt energy. So we are interested that what is the entropy before and after the equilibrium. So this is the first case, represents the case of before equilibrium, when there are three particles associated with this block and one particle associated with this second block. So now let's calculate the entropy for this first block. You will see that there are three quantas associated with this system A, and there are four particles in this system. So you can place this first quanta either on this particle, or third one, or fourth one. So there are four different ways in which you can place this first quanta in this system. It means that there are four different arrangements. And similarly, when you place this uh, quanta on any of these uh, molecule, for the second quanta, you will see that you will have three different arrangements. That is either let's suppose that the first quanta is placed on the first particle. Now you have three particles on which you can distribute this second quanta. So to distribute the second quanta, there are three possible arrangements. And similarly, when the second quanta has been placed, let's suppose on the second particle, you have two particles without any quanta. So for in order to place the third quanta, it means that you can have either this third quanta on third particle or on fourth particle. So there are two different ways in which you can place this third quanta. So what we are assuming in this problem is there that each particle can have only one quanta associated with it. So it means that the total ways in which you can distribute this three quantas between these four particles is four for the first particle, 3 for the second particle, and 2 for the third particle, which is equals to 24. And similarly, since for the second particle there is only one quanta associated with the second particle, so this one particle quanta is either associated this with this first particle, second, or third, or fourth one. So it means that there are four ways in which you can place this quanta on these particles. So W for this second state will be equal to 4. So now let's calculate the entropy for both these blocks separately, and let S1 be the entropy for this first block. So S1 is equal to Kb log of W, and W is equal to 24 in this case, and similarly S2 is equals to, which is the entropy of this second box, is equal to Kb log of 4. So putting the log values of log of 24 and log of 4, you will have a total entropy of 4.55 kb. So this is the entropy of this total system before the equilibrium. Now let's understand that when the equilibrium has been established, and that energy has been distributed equally on both these objects, that is that there is a 2 electron volt is associated with this first object, and 2 electron volt is associated with the second object. In that case, now let's find out the entropy after the equilibrium it has been established. So in that case, there are two particles associated with this first box. So it means that there are four different ways of placing this first particle, and whereas this second quanta, so in order to place the second quanta on these four particles, there are three different ways. So it means that there are 12 total different ways of placing these two quantas in these between these four particles. And similarly, for this second object, since again there are four particles and two quantas associated with it, and again there will be 12 different ways in which this can be done. So the total entropy, that is S1 prime for the first object, is equal to Kb log of 12, and the entropy for the second object Kb log of 12, and their sum, the total entropy, will give you St prime equal to 4.96 Kb. In previous case, when the equilibrium was not established, you have a total entropy of 4.55 kb, and when the equilibrium has been established, the entropy is equal to 4.96. It means that after the equilibrium, the entropy of the system has been increased. So we can say that for an isolated irreversible system, the entropy of a system always increases. So that is when a system goes from a non-equilibrium state to an equilibrium state, the system always increases the entropy of the system. So at the end of the lecture, let's discuss about the third law of thermodynamics. So now, from first law, we learned that the first law is about the law of conservation of energy, which tells us that the energy of a system will always remain conserved. But it does not tells us about the physical insights about the system, that why heat always moves from a body at higher temperature to the one at lower temperature, and that physical insight is given by the microscopic version of the second law of thermodynamics, that a system wants to move towards the direction of increasing entropy. And what is happening there is that the system is what is system basically trying to do is that the system is trying to move towards the most probable state of the system. So that's it for the second law of thermodynamics. So now let's discuss uh, the third law of thermodynamics. Uh, Third law of thermodynamics basically defines that what is the absolute zero of temperature, and it also ties together the concept of entropy and temperature. We know that the coldest place in the universe is Boomerang Nebula, uh, present in the Centaurus constellation. The temperature of this Boomerang Nebula is around 1 Kelvin. So this is the coolest place present in this universe. We can also further lower the temperature below 2 Kelvin artificially. That is, the scientists have been able to get even colder than that by using the method of laser coolings, where they have cooled sodium and potassium particles even to 500 nanokelvins. But even they could not get the absolute zero. So the third law of thermodynamics is defined as uh, uh, tells us that the third law defines what the absolute zero is, and it tells us that the entropy of a perfect crystal approaches zero at a temperature of absolute zero. It tells us that we cannot achieve the absolute zero of temperature. It also tells us that the entropy of a perfect crystal always approaches zero at absolute zero. How we can understand that why the entropy of the system is zero? Again, we can use the Boltzmann law in this case, which that is the microscopic version of Boltzmann, which is equal to S is equal to kb log of W. And since in this case you have that almost your crystal is at near the absolute zero of temperature, it means that all the particles are frozen, so they cannot move to get move from their places. So it means that there is only one possible arrangement for that crystal. So it means that W in this case will be equal to 1. So the entropy of the system for such a case will be equal to S is equal to kb log of 1, and we know that log of 1 is equal to 0. So we can say that the entropy of a perfect crystal approaches zero at absolute zero of temperature, and that's the third law of thermodynamics. An important idea to note is that the absolute zero may not be able to achieve experimentally, as we know from the second law of thermodynamics, that the object which we are trying to cool is always taking heat from the environment. So that's why we cannot have the lowest possible temperature. We cannot have the absolute zero of temperature, because that system is always taking heat from the environment. So and that's all about the third law of thermodynamics. So that's it for today's lecture. Thank you.